Good afternoon. Welcome to my presentation. The topic is the performance of a heuristic uplink radio resource assignment algorithm for LTE Advanced by Jairo Garcia, Maciek Muelbersen, and Kai Hensen. This is the index of the presentation. First of all, I'm going to talk about the motivation, and then the problem description. The third part is about the resource assignment algorithm. And then we're going to explain the scenario that we use in the simulations, and then the results, and at the end the summary, conclusions, and outlook. This is the motivation of the topic. Three very important points here. The cell spectral efficiency is a key performance indicator. The reduced distance increases cell spectral efficiency. The high interference in reduced one scenario. We need a resource management to mitigate the interference. We can see here the two cases. The first case, we can see the reduced 3 uplink with low interference, approximately a meter from cell center. And here the other case with the reduced 1 uplink with high interference from different user terminal positions. This is a very simple example, used with 2 user terminals per each base station. We have here the resource blocks. Each resource block has a color who represents the resource block from the user terminal 1 and from the user terminal 2 in this case. And also here, the green is from the user terminal 1 of the base station 2 and the red from the base station 2. In this case, we have only 2 possible scheduling combinations, and which one is better? We want to maximize the cell spectral efficiency, and we choose the maximum SINR. This is the same example, but with 1 user terminal more. First of all, we calculate the SINR using the reception power, the transmission power, and the path loss. In this simple example, 2 users are transmitting at the same time, and at the end we obtain this equation of the SINR, and we can omit the noise. At the end we obtain only that the SINR depends only on the distance of the interference and the distance of the signal. For the calculation, we use the subtraction of the path loss interference and the path loss of the signal. We can see here that this is the fixed value in the matrix. Also for the second and also for the third user. We repeat the same procedure for the second user, who is interfered by other users transmitted at the same time. Also for the third one, and at the end we obtain one matrix with the signal in the columns and the interference in the rows. We repeat the same procedure for the second system, and at the end we obtain 2 matrices with the SINR. The next step, after we obtain the SINR, is do the mapping into data rates. For this case, we choose 2 ways. One is the analytical way, using the Shannon-Harris theorem, and the other way is using a table with different kind of modulation and coding schemes. In this case, we use QPSK, 16 QIM, and 64 QIM. Our goal is to maximize the cell spectral efficiency. For that, we maximize the data rate zoom. We do the zoom in this way of 2 data rates. Each value of the matrix represents the rate of base station 1, user terminal 3, interfered by base station 2, user terminal 2, and also here. At the end, we obtain only one matrix with the rates of the base station 1 and the base station 2 in the rows and the columns. After that, we apply the resource assignment algorithm. The Brady algorithm, in this case, looks for the maximum value in all the matrices. In this case, it's 1.59. as I said before, this value is composed by two user terminals who are transmitting at the same time. In this case, user terminal 1 from base station 1 and user terminal 3 from base station 2. And then we schedule those users, and we remove of the matrix all the other users, and we continue finding again the next max value. In this case, at the user terminal 3 and user terminal 1. And then we remove again of those users. The last value in this case is 0.1.9. And all the users has been scheduled. This is the complexity of the algorithm. Is O n at the power of 3. N is the number of user terminal per system. This is the set of values obtained for the gradient algorithm. The self-spectral efficiency is calculated like this. 9.6 resource blocks per user terminal. In this case, for the simulation, we use 10 user terminal per base station, and the uplink use 96 resource blocks divided by the number of users is 9.6. The system bandwidth is 20 megahertz, and we zoom the database values here, and we obtain 1.99 bits per second per hertz. And then we compare these results with an optimal algorithm who finds the optimal values. The complexity of the algorithm is O n to the power of 4, and we use the Hungarian algorithm. The number of operation runtimes depends on the value in the matrix. We can see the difference. It's not so big. Okay.
Okay.
This is the scenario.
Thank you. Okay, so I will continue. My name is Maciej Bühleisen. So what you've seen before was just an example, basically using three user terminals, and here is the scenario we've actually simulated. So besides all the cellular scenarios we've already talked about today, there's an even simpler standard scenario standardized by the International Telecommunication Union, the so-called indoor, the IoT Advanced Indoor Hotspot scenario. So here we have only 2 base stations, as we mentioned before. Those are 60 meters apart, and well, usually we deploy 20 user terminals randomly in the whole scenario. But for our work at the moment, we have to have a same number of user terminals per base station. So here we equally distribute 10 user terminals per base station. Well, we use 100,000 drops, so on each drops the 20 user terminals are distributed at a different position. Why this high number, I will explain later. So we use a quite simple channel model here, so we only consider path loss, so we do not consider a small-scale fading, which is in the original model. And we also do not consider shadowing. This is also due to our limitation at the moment that we have to have equal number of user terminals per cell. So, well, the first results I'm going to show you are with free space propagation, so a path loss coefficient of 2, and later we're going to change the path loss coefficient. So, the algorithm we want to compare is the optimal assignment we showed at the end. The greedy algorithm we have presented in the example, and we want to compare it to a completely random assignment. So this is basically what the LTE calibration scenarios tell us to do. Well, just take the user terminals by some kind of number by the moment where they're associated, and then just schedule them. So this ends up in a completely random assignment. And we want to see the throughput distribution, the cell spectral efficiency, and also want to take a look at the algorithm runtime. So the first result here is, as we also see sometimes today, is this cumulative distribution function of the throughput. So for each of the 20 user terminals, I take the achieved throughput, and then I take an average distribution over all the 100,000 drops. In blue, you see the optimum, the results for the optimum assignment. In red, the proposed the results for our proposed greedy local search algorithm, and in green the results for a totally random assignment, so no optimization applied. And actually, what we see just starting at 30%, so only for the best 30% we actually get a gain. Well, this, of course, we try to maximize cell spectral efficiency, and this often, of course, goes, does not go well for the bad users. So actually, for the worst 30%, it is better to use a totally random assignment. But for the other 70%, we see a gain if we have an optimal assignment, and we see here the red line actually comes very close to the optimum. This is if we use the 13 modulation coding schemes for optimization. So this is why I actually see only 10 steps, because we do not have any SANR values below 0, so we end up with 10 different modulation coding schemes we can have. On the right side, you see the same results if we apply the Shannon theorem to map our SANR values to data rates. And well, here, as we see nothing. So it's like half of the time the random assignment is the best for the bad users, of course. Then, of course, the optimal assignment is very good for the 50% best users. Well, and the proposed greedy algorithm is somewhere in between. So it's really hard to tell if we actually increase the cell spectral efficiency here or not. Okay, that's why we have here some more results showing our gain in spectral efficiency over the path loss coefficient. So in those close reuse 1 scenarios, it's mainly if we increase the path loss coefficient, we basically we decrease the interference, since the interference is highly attenuated. So those results are relative to the random assignment. So in red, our proposed greedy algorithm, and in blue, the optimum which we can actually achieve. So this is the results for path loss coefficient 2, as we've seen before. So we see we get 4% gain, or even 4% gain in cell spectral efficiency with the greedy algorithm. The optimum assignment could give us even 70% gain. And as the path loss coefficient increases, the possible, the performance of the greedy algorithm decreases a little, and the performance of the optimal algorithm starts increasing a lot. But then at some point it starts dropping again. At some point the interference is attenuated so much that actually all users are using the best modulation coding scheme, so there's not much more I can gain. And at some other point I actually cannot serve the whole cell anymore. So this is again if I use the modulation coding scheme mapping. Then amazing result as we use Shannon theorem-based mapping. So please note this. So this is now 10 to the power of -3. So now we are just within a percent. So the highest gain we can get here with the optimal algorithm is just 1.3%. Well, and with our greedy algorithm we get 0.8%. So we can conclude here between optimum and greedy we don't gain much, and we do not gain much at all. So this is just by using a different approach of mapping SANR values to modulation coding schemes. Well, one of the key reasons is when I have discrete modulation coding schemes, there is a chance when I optimize that actually one user gets a higher data rate, while other users do not actually change their data rate because their SANR drops down a little, but they still remain above a certain threshold. Okay, just one last results are the algorithm runtimes. Actually, when we started the work, we thought that this assignment problem was, NP hard, we have to use brute force, but then, okay, we find out this is known from operation research, this can be solved in O and 3 by previously mentioned Hungarian method. But this method actually, the runtime highly depends on the values in the matrix. So whenever I have different user terminal positions, I have different SANR values and data rate values in my optimization problem. So the runtime can reach from here it goes from 2 milliseconds all the way up to 6. And then it highly depends whether I have the modulation coding scheme approach or the SANR approach, because here with the Shannon mapping there's even more different values appearing in my matrix. while for our proposed greedy method, well, the runtime is mostly around 300 microseconds. So this is especially below the duration of an LTE frame or the transmission time interval. Of course, this was done on our Pentium machine, so it cannot be directly compared to real system hardware. But most importantly, it is pretty much deterministic, so it just depends on the number of terminals. And of course, this is a two-cell example. If I coordinate more cells, of course, I will need more runtime. Okay, so I'm coming to an end. So what we have done here, we have presented a heuristic algorithm for radial resource assignment in the uplink. And well, we've evaluated the performance of the algorithm, mainly looking at cell spectral efficiency, but in the written work you can also find some remarks on the cell edge user spectral efficiency, so the 5% here. So well, by our algorithm we can increase the cell spectral efficiency by up to 5%. And well, the actual gain you can get depends on, well, in this case, of course, in our research on the channel model, and in reality, it depends on the interference levels. And well, what we've also found out that, well, if the algorithm uses the Shannon-Hartley formula to map SNR to data rates, we almost get no gain, and this is really remarkable because most research, or a lot of research work focusing on optimization, either the assignment problem or power control problems, uses this formula. So it would be really interesting to redo this work using real relation coding schemes, but then often you don't have a closed solution anymore. Okay, so this was just a starting point, so there's a lot to go on. So what I can tell you for sure, this optimal solution in n to the power of 4 times is not possible if there's more than 2 cells, or at least from what we know is not possible. From this point on, there's only heuristic algorithms. The algorithm we have presented, a very simple one, it will for sure work with more than 2 cells. Then it's not just a matrix, but it becomes a multi-dimensional matrix. And then we of course want to find out how much can we gain compared to a random assignment. Well, just a drawback at the moment, we rely on having the same number of user terminals in each cell at the moment. Of course, this needs to be changed. We would like to estimate actually the signaling overhead for the IDE. But right now, the only thing I need as input is the path loss. But of course, the path loss not only to my serving base station, but also to the other base stations. But maybe this is available from handover decision signaling or measurements we have right now. And of course, well, most research focuses on transmission power control, so this is something we also is want to have a look at. Okay, thank you very much, and I'm waiting for questions now. Okay.
Your algorithms depend on the path loss you stated. Does this also have to include the radial fading, or is this more an average path loss? Because it can change very fast, and then you have to transfer all this radial fading data to the next base station, and it's time critical.
Yes. So for now, we assume that this is average over time, so we don't consider this. But of course, it's something we want to look into, like how sensitive the algorithm is actually to channel mismeasurement, because we already see we don't gain much, and well, maybe we lose, or maybe we even have negative if we have misestimations there. Because of course we also hope to one day do voice over IP with that, because well, it's easy if we have these full buffer models, but if it keeps on changing all the time, so I have different active users, then I really need fast algorithms, and then well, this is actually the goal, to see what are the active voice over IP terminals and to really reschedule in every frame. And then I cannot rely on averaging over a long time.
Yeah, what's your first assumption, or how do you know the path loss?
The path loss to the path loss of the terminal served by me, well, so of course it's kind of a TDD assumption, then it's channel reciprocity, so I can obtain the path loss. Well, and for the others, hopefully from handover information. Yeah? So if I know the power of my pilot signals and I know my received power of those pilot signals, then I can estimate the path loss also to the other base stations, not only to my base station. But of course, if the channel isn't reciprocal, I have to transfer this information. Most hopefully one day we will do the whole baseband processing at one central place, and then we have everything available anyways, but this is of course the future.
Okay. Thanks a lot again.
Thank you.